I'd like to repeat problem 9.1, except this time I'd like to use the cold air standard model to illustrate numerically how would we solve problem 9.1 using the cold air standard. And then let's compare the numerical results for air standard versus cold air standard. So let's get started. Here's the exact problem statement for 9.1, except you can see that I'm replacing the air standard assignment with cold air standard. Beginning of a compression process of a cold air standard Otto cycle with P1 equals 100 kPa, or 1 bar, and T1 is 300 degrees K. The compression ratio is 8.5, and heat addition per unit mass of the air is 1,400 kilojoules per kilogram. What you need to determine is the net work, the thermal efficiency, the mean effective pressure, and the maximum temperature of the cycle. Now, there's going to be a lot of repeat slides in this presentation because I've just gone through and provided a solution for the air standard. So let's look at what's similar and what's different. Okay, so keywords and clues should look familiar. Now, what does cold air standard mean? It means model the air as an ideal gas, but this time with a constant specific heat. In other words, Cp and Cv are held as constant values. And so what does that translation mean? It means that we're going to go to table A21 to get a single value for C sub V and also K, and we're going to hold it as a constant value. Otto cycle, just like previous, you should be able to create the PV diagram from your head for the Otto cycle based on your understanding of how a spark ignition engine works. And here, again, I'm going to try to quickly go through and explain, how can you generate this pressure specific volume diagram basically from your head, knowing just some basics about a spark ignition engine. Okay, and so here, of course, is the sketch of the very traditional piston and cylinder internal combustion engine model. What's the closed system? Well, it's the air contained within the piston and cylinder. Here's a spark plug that's going to be utilized. And of course, you remember the, let's see, when the piston is all the way down at the bottom, that's called bottom dead center. That's the maximum volume of the air in the piston and cylinder. And the minimum volume, of course, is going to be when the piston's at top dead center. Okay, so there's the sketch of our system. Well, how about generating a PV diagram quickly? Let's see, process 1 to 2. That would be the compression stroke in which the piston is at bottom dead center, maximum volume, and it starts to move and compress the air as it moves toward top dead center, so that air in a reversible and adiabatic compression process, the pressure's increasing and the temperature's increasing, reversible adiabatic process. Then with the fuel in the air inside the system, we hit a spark plug. We hit a spark and there's instantaneous combustion. And as a result of that instantaneous combustion, there's not enough time for the piston to start moving back towards bottom dead center. So the pressure and temperature within the system immediately increase to P3 and T3. That's our heat addition model. Then 3 to 4, reversible adiabatic expansion, also known as the power stroke of the piston and cylinder for our internal combustion engine. That's where we're producing power, okay? And then finally, for our thermodynamic model, we're at state 4 at bottom dead center. We're simply rejecting heat from the closed system. You know good and well that in the physical system, we go through an exhaust process where we exhaust the exhaust products out of a valve, and then we come back and we pull in clean air from the surroundings in the intake stroke. But Our thermodynamic model is well defined here. 1, 2, 3, 4, 1. Now, one thing I forgot to mention in the air standard model is you can visualize the net work done by the area enclosed within this pressure specific volume diagram. So that's a visualization of the net work. Okay. Some additional keywords. The compression ratio is 8.5. That means that for the internal combustion engine, compression ratio is the maximum volume, bottom dead center, divided by the minimum volume, top dead center volume. Another sort of interesting part about this particular homework problem is that what's given is the heat addition per unit mass, 1,400 kilojoules per kilogram. And that's what makes this problem a little different than the example problems given in the textbook, in which there's various derivations and formulas utilized to solve it. This is a little twist. This problem 9.1 is a little twist on the traditional given information. Okay, what's the next one? What do we want to find? We want to find the network. You've got a visualization of that on the PV diagram. The thermal efficiency, that's the energy sought over the energy that costs. The mean effective pressure. Now, the mean effective pressure is not something I had off the top of my head, even coming in from Common Sense 101. So I was introduced to the concept of mean effective pressure as a performance measure for internal combustion engines when I got into my thermo classes. So even I will need to refresh my memory on the definition of mean effective pressure. And then finally, part D, the maximum temperature of the cycle. Now, if you study on the given information, you study your sketch, you're going to see that you kind of need to do part D first in order to do other parts of the problem. And so that's going to be a key to drive towards determining the maximum temperature in the cycle, nearly the first thing we do. If you need a little more refreshing about the difference between air standard and cold air standard, when you see those two phrases, you need to quickly understand how are they different. And so I try to explain this in a 28-minute video. If you go to my Jay's Toolbox YouTube video and look at the air standard cycle playlist, you should be able to find this air standard intro. Another quick reminder, early in the semester, you were dealing with capital Q in and capital W out. In kilojoules, Q in, W out had units of kilojoules. And as you went through the course a little further, either your instructor and certainly the textbook would divide capital Q in and capital W out by M, the mass of the closed system, mass of the air in the closed system, and come up with this variable called little q and little w. So recognize the units of little q and little w are kilojoules per kilogram, and that's what's given in the problem in terms of the heat addition, little qh. Another reminder, for this solution, we're going to use the cold air standard model. We're going to go to table A20, and we're going to tabulate a single value for K and a single value for CV at the inlet temperature at T1. Okay, and so I've cycled what's the specifics about cold air standard, in other words, ideal gas with constant specific heat. Well, for any ideal gas, remember that Cp minus Cv is equal to R. And also the definition of K. What is that K thing? It's Cp over Cv. That's the definition of K, specific heat ratio. For any ideal gas with a constant specific heat, the change in internal energy is, well, the integral of Cv dt. And if Cv is a constant, we pull it out of the integral. And so the change in internal energy is simply Cv times delta T, T2 minus T1. Another very powerful fundamental that's been derived in your textbook is for an ideal gas with constant specific heat undergoing an isentropic reversible adiabatic process, PV to the K is constant. Now that can be derived. That's not just a formula that you can accept. You can derive this with what you've covered in your class so far. Well, what does this mean numerically in terms of actionable? Well, it means that P1V1 to the K equals P2V2 to the K. That's what that means. That's what PV to the K equals constant means. So, but it's only for isentropic process, constant specific heat, ideal gas. If you need a little refresher in some of the details about Otto cycle calculations, again, go to Jay's Toolbox, the playlist, Air Standard Cycles, and you can click on some more information about the Otto cycle. Where is T max? I'm going to suggest that you can, by your eye, you can visualize that T max occurs at state 3. I've drawn in 4 isotherms on a PV diagram, isotherms, 1, 2, 3, 4. Now those 4 curves are hyperbolas. Those are lines of constant temperature. So for any ideal gas, P times little v equals RT, doesn't it? So let's see, RT. For constant temperature, RT is a constant. So PV equals constant. Okay, so let's see, PV. That's kind of like XY equals constant. That's a hyperbola. So these 4 lines represent 4 lines of constant temperature. And so with your eye, you can see that the highest hyperbola occurs at T3. So therefore, you immediately know that I'm looking for T3, and that's going to be, let's see, that's going to be part D of the problem. So we're going to plan our work, and let's study what kind of work values do we have. We went through this with the air standard cycle, so I'm going to try to blaze through a little more quickly. Let's see, 1 to 2. Isentropic compression. Work is the integral of PdV. I'm integrating right to left. The area under the curve is a negative number. Okay, we're going to be able to do that. We're going to be able to solve for that. Let's see, 2 to 3. The area under the curve, integral PdV, that's 0 for the heat addition model. 3 to 4, we're integrating left to right. The area under the curve is the work done for this reversible adiabatic process 3 to 4. It's going to be a positive number. 4 to 1, we don't even have to worry about the work there. Area under the curve 4 to 1, no area under the curve. So we've only got to worry about computationally evaluating 2 work terms. And then the other part is, you see that the net work then visually is the area enclosed within this Otto cycle PV diagram. And let's see, little v1 divided by little v2, that's given. It's 8.5. That's called the compression ratio. Capital V1 over capital V2 equals little v1 over little v2. A reminder, for our basic cycle schematic on the Otto cycle, remember, what are we trying to do? The thermal efficiency is W net divided by QH, the heat added, energy sought over the energy that costs. And so look, once we've got W net, QH is given, we can immediately calculate the thermal efficiency. The mean effective pressure, even I have to go back to the textbook and remind myself that this measure of performance, the mean effective pressure of this piston and cylinder is described as the net work for one cycle, kilojoules per kilogram, divided by the displacement specific volume, cubic meters per kilogram, so that we get units of pressure. Basically, it'll be kPa, kilonewtons per square meter. Okay, let's start off with, so we're going to plan our work. We'll set up a little table. Let's see, Q in, we'll tabulate Q in values, W out values, 1 to 2. Reversible and adiabatic. No heat in, 1 to 2. 2 to 3, QH, well, that's given. That's the heat added. 3 to 4, reversible adiabatic, 0 Q in, and QL is 4 to 1, and we're not going to have to worry about that. How about work terms? Process 1 to 2, work is a negative value. 2 to 3, I'm going to write 0, immediately write down 0. 3 to 4, the work done, positive value. 4 to 1, it's 0. That's going to be immediately what enables me, if I add these numbers up, that'll give me W net, immediately get the thermal efficiency. And let's see, what else are we going to use for our analysis? We're definitely going to use PV equals MRT, or in other words, P times little v equals RT. We're going to treat CV as a constant and K as a constant. So when we need to evaluate any change in internal energy, all we have to do is use CV, some number, times delta T. Okay, and so you get the idea. All right. Well, there we go. Let's see. I think we're just about ready to start putting pencil to paper. Where will we start? We study the problem and we discover that P1 is given, little v1 not given, R we've got, it's R for air, and T1 is given. So the first thing we'll do logically, we're sort of driving towards T3. We know we got to figure out what T3 is. We'll start at state 1 and we're going to try to work our way up to state 3. So we'll get V1 first and see where we go from there. Okay. So let's see, what else are we going to do? Once we get V1, you see that it's going to be easy to find little v2. Now, we know that process 1 to 2 is reversible and adiabatic, so we will use P1V1 to the K is P2V2 to the K. That looks pretty, I think you can see this, right? So you can see what's given and what's not known. We can solve for P2, but look, once we've got P2, we can use the ideal gas law to find T2, okay? Then we'll use the first law to figure out what T3 is, and we'll go from there. Once we've got T3, look, once we have T3, we know what V3 is. Well, that's equal to V2. If we've got V3 and T3, we'll use the ideal gas law to find P3. That's going to enable us to move on then on further down, analyze process 3 to 4 to get the work out from 3 to 4. And then basically we're done. So it is my hope that you're going to see that this solution numerically is going to go a little faster than using air standard or variable specific heat. So you can see we're going to use the first law for the processes in order to determine temperatures we need. All right, so now we're ready to put pencil to paper, and by heart I need R for air. R for air. If you don't remember, if you don't have it in your head, at least you remember R bar is 8.314 kilojoules per kilomole degree K. I fixed my blunder from the first video, you'll see, and the molecular weight of air is 28.97 kilograms per kilomole. R bar over the molecular weight then is 0.287 kilojoules per kilogram degree K for air. So if you don't know that off your head, you can easily determine what R for air is. Okay, what else do we know? P1 given, 100 kPa. I write down 100 kPa rather than 1 bar because I know that working in kPa is certainly where I need to be when I'm working on SI problems. T1 in absolute temperature given 300 K. Compression ratio 8.5, that's V1 over V2. Okay. So we'll solve flat out for V1, 0.8610 cubic meters per kilogram. V2, let's see, V2, we've got 0.1013, that's just V1 divided by 8.5. Okay, then where are we going to go from there? Let's see. We got to go to table A2. I had a mental lapse there for a second. What do we do next? We're going to we need a value for K for our isentropic relation, and we need a value for C sub V for our first law. So we'll just go to table A20, and we're going to evaluate our constant values at T1, 300 degrees K. So we've got 0.718, kilojoules per kilogram degree K on CV, and 1.4 for K, CP over CV. All right, so we're going to write that down in our solution. We're headed towards, we're saying, gosh, I've got to figure out how do I get to T3? How am I going to get that? Well, of course, one thing you could do that I don't recommend is fishing through some formula in your textbook and, oh, here's a formula to work, I'll write it down. That's not going to help you get ready for a quiz or test. This approach will. Okay, we know that we've got process 1 to 2 is reversible and adiabatic. We've got an ideal gas, constant specific heat. So we will write down in our solution P1 V1 to the K equals P2 V2 to the K. So let's see, we've got V1 over V2. We've got K. We've got P1. So I'm going to solve for P2 and then see where I go from there. So sure enough, P2 is 2,000 kPa. All right, great. All right, well, let's see. Okay, I've got P2. Well, I've also got V2. I just found what V2 was. I calculated it, didn't I? And so if I've got P2 and V2, I can use the ideal gas relationship to get T2. All right, here we go. Ideal gas law. T2 is P2V2 over R. P2V2 is equal to RT2, all right? And so numerically, T2 is 706.1. Okay, so now I've got T2. I'm trying to figure out T3 though, but at least I'm a little closer to state 3. What are we going to do now? We think about it, we say, well, we're given the heat added from 2 to 3. What if I wrote the first law from process 2 to 3? Can I get how can I get to T3 that way? I think the answer is yes. So we're going to write the first law for, well, wait a minute. I got to back up a little bit. We're driving for T3. Let's do a little side part first. We know that we're going to need to calculate the work out for process 1 to 2. Okay, so we just found T2. Let's write the first law for process 1 to 2 to get the work before we move on to state 3. Okay, so that's kind of the way I work through this. There's nothing to have kept you from finding T3 first, but this is the way I went ahead and solved the problem. I said, okay, I've got T1. I just found T2. I've got a value for CV. I'm going to write the first law for process 1 to 2. Let's see, Q in from 1 to 2, that's 0. Minus W out from 1 to 2 is equal to U2 minus U1. And so let's see, I'm going to flip the sign on the first law. So W out from 1 to 2 equals U1 minus U2. I've got constant specific heat. So U1 minus U2 simply equals CV times T1 minus T2. Plug and chug. And so W out from 1 to 2 is negative 291.61 kilojoules per kilogram. So it's a little side project we had. We'll put that off to the side. Okay. Next thing is we're going to write the first law for process 2 to 3 because we need to determine T3. That's what we're looking for. That's going to be part D. So part D, let's say first law. We know Qn, we know T2, we know C sub V. And so here in my solution, the first law for the process 2 to 3, Q from 2 to 3 minus the work from 2 to 3, that's 0, equals U3 minus U2. Well, that's just for constant specific heat. That's simply CV times T3 minus T2. Well, plug and chug again. Wow. Immediately solve. T3 is 2656 degrees K. So now we got part D. And we're halfway there on net work because we had that little side project of calculating the work from 1 to 2 that turned out to be a negative number. Now we've got so let's see, we know we need the work from 3 to 4. So we're going to need T4. We know we're going to use the first law. We don't know T4, so how will we find it? We recognize that process 3 to 4 is isentropic, reversible adiabatic. Q equals 0. Okay, so let's see. So I decided to circle And just to refresh my memory on what we've got here, I wrote down the fundamental in my solution. P4V4 to the K is P3V3 to the K. That's the isentropic relationship, ideal gas, constant specific heat, constant K. Okay, and so I see I've got all of these things written down. See, K I've got, V4 I have, V4 over V3 I have, okay? And let's see, what did I not have? Oh, in my solution, I had T3. I also know that V3 equals V2. I need to find a P3, don't I? So I use the ideal gas relationship to get P3, 7525.3 kPa. So I needed P3 in order to go into my isentropic relationship. Again, plug and chug, solve for P4, 376 kPa. Okay. Wow. So let's see. I've got P4. How about, do I have V4? Yeah, that V4 is just V1. V4 equals V1. So I can solve for T4. T4 is 1128 degrees K. You see where we're headed? Let's see. Now that I've got T4, I can now write the first law for process 3 to 4. Okay, and so let's see. First law, I've circled it again, refresh my memory. Let's see. Qn from 3 to 4, well, that's 0, reversible adiabatic, minus W out from 3 to 4 equals U4 minus U3. We got to flip the sign. Work out from 3 to 4 is U3 minus U4, constant specific heat. So U3 minus U4 is simply CV times T3 minus T4. Plug and chug once again to get work out from 3 to 4, 1097 kilojoules per kilogram. Getting very close to being finished with this problem. I've got both of my work terms. I add them together to get 805 kilojoules per kilogram. One thing I didn't point out on the air standard solution was the visualization of W net. So the visualization is the area enclosed within this PV diagram cycle of the Otto cycle. There it is. So there's a visualization of W net. Okay. So we've got part A, 805.2 kilojoules per kilogram. Thermal efficiency. Well, we just got W net. QH was given. Thermal efficiency, 57.5 thermal efficiency, 57.5% thermal efficiency. Energy sought over the energy that costs. I have to refresh my memory on mean effective pressure, MEP. Net work, just found it, kilojoules per kilogram. Displacement volume, well, that's going to be little v1 minus little v2. We have all those values. So again, plug and chug, the mean effective pressure is 1060 kilonewtons per square meter. If you've got to check your units, well, that's kPa. And the textbook asks for the mean effective pressure in bars, so we'll divide by 100 to get 10.6 bars is our mean effective pressure. And I think we've got it. And so here's the recap of our Otto cycle analysis using air as an ideal gas with constant specific heat. And there's those numbers. We just found them, okay? It makes sense to compare our numbers using cold air standard analysis to the air standard analysis. And here is that comparison. Here's a comparison table. So I went back to the previous solution and tabulated the air standard values. Better move my picture here, okay? So let's have a little look at what we've got. There are numerical differences, aren't there? So these are definitely not the same. What kind of things do we see? We see that we've got, for the air standard, we've got a little lower net work, a lower thermal efficiency, a lower mean effective pressure, and a lower maximum temperature in the cycle. And so many students will say, well, what's the right answer? Gosh, you studied the same exact given information using two different models. What is the right answer? Well, I hesitate to say the right answer is blah, blah, blah. But one thing I think I could say is that, look, we have a huge variation in temperature, don't we? But from max to min. Our lowest temperature is 300 degrees K. Our maximum temperature is somewhere between 2200 and 2700 degrees K. A huge variation in temperature. And you remember that for ideal gases, properties, even like specific heat, are temperature dependent. And one thing we talked about holding specific heat constant would be for problems where the temperature doesn't vary dramatically. And so to answer the question, which would be more accurate or which would be favored for this particular problem, I would have to, as a practicing engineer, I would have to say that the air standard analysis would be favored as being more accurate model of the real world than the cold air standard for this problem. And so that's kind of an interesting learning. I found it very interesting to solve the same homework problem using two different models for the ideal gas. Let's see, cold air standard, holding C sub P, C sub V, and K as a constant value evaluated at 300 degrees K. We got these numerical results. Then before that, we said air standard, we're going to treat the specific heat as a variable, and we're going to get all of our air properties from table A22. In other words, that's modeling with variable specific heat. And so I'm a little more comfortable with these numerical results using the air standard analysis. Okay, so I hope that helps in a couple of ways. One is to illustrate how would you analyze an Otto cycle from scratch and not depend on Otto cycle formulas given in the book. So I do want to suggest that really learning how to analyze these air standard cycles using the fundamentals is a far better approach than simply copying and pasting specialized formulas out of the textbook. It's a great way to prepare for quizzes and tests when your instructor gives you a made-up air standard cycle that's not covered in your book where there's no formulas. That's a classic thing for an instructor to do. That's certainly what I do on my quizzes and tests. And then another thing, working the two separate examples, is to illustrate why and how do you get numerical results that are different depending on your ideal gas model. So I hope that helps, and I'll encourage you to look at the next video where I believe I'm going to try to illustrate an air standard Brayton cycle.